Okay, good morning to everybody. I am Stefano Rodinò. I'm very glad to be here today to present this work about optimizing the dimensional parameter of a 3D printed active composite beam by using as a material with a nonlinear analytical model. Here is a short outline of my presentation. In particular, I will start from the motivation, and next I will introduce some functional properties that we are interested in this work of the active material, that is shape memory alloy. And moving on the presentation, I will present some result of the experimental characterization that is needed to predict which is the behavior of this particular type of material. And after this characterization, I present the analytical model that we want to propose to predict the bending of an active composite beam. And finally, we want also to validate this analytical model by providing an analytical versus experimental result with design and prototyping phase. Okay. So this preliminary work is made in collaboration with the Stellantis group, and in particular, the aim of this project is to design adaptive aerodynamic surface by using SMA material. This is possible by using the shape morphing principle that consists in placing the active material, that in this case is an SMA material, as far as possible from the neutral axis of the section to increase the bending of the active composite. And by actuating this material, it is possible to perform a deformation of the full profile of the active composite beam in this case. This type of material, in particular the active composites, have attracted a lot of interest in the recent years because they are numerous advantages, but also you have a lot of problems, especially in terms of thermal interaction between the polymeric matrix and the shape memory material. The aim of this study is to develop an analytical model for predicting the curvature of an active composite material, and also to we want also to identify which are the best 3D printed material to product, for example, some demonstrator for this application. And finally, we want also to propose an experimental validation of this analytical model by the production of some functional demonstrator. Shape memory alloy are a particular class of material that have a different functional properties, in particular the shape memory effect and the pseudoelasticity. And this material consists in two different phases. One is austenite and the other one is the martensite. In this work, we are also only interested in one of the functional properties, that is the shape memory effect. And this property is the capability of the material to recover large deformations that are pre-impressed during the cold phase when the material is heated above the transformation temperature that is named austenite finish. To predict the behavior of this particular material, a lot of characterization are necessary, but in this work we are focused only on to obtain the mechanical properties of the two different phases by conducting two types of tensile tests. One when the temperature is less than martensite finish, and one when the temperature is above the martensite finish. And another aspect that we are interested in is the connection between the transformation temperature and the applied stress on the SMA material. And this can be done by obtaining the phase diagram through some constant stress recovery. The first experimental characterization that we have conducted is the tensile test when the temperature is less than martensite finish. In particular, from this test, we can obtain the elastic properties of the martensite, but another important aspect is that we can also obtain the maximum transformation strain that the SMA material is able to recover during the activation. Another important test is to estimate which is the elastic module of the austenite by conducting a tensile test when the temperature is above the austenite finish temperature. Another experimental characterization has been made to conduct some constant stress recovery test. In particular, a special experimental setup has been made by assembling this setup with a thermal camera, a displacement transducer, and some hanging calibrated masses that can bring the wire to recover under a constant stress. By this test, it is possible to obtain the hysteresis loop of the material for several levels of constant stress. And from this data, it is possible through the tangent method to obtain the 4 transformation temperature for each level of constant stress applied. From this data, by interpolating this data, it is possible to obtain the phase diagram of the material. And with this phase diagram, we have all the relations that connect the transformation temperature to the applied stress. Okay, at this point at the end of the experimental characterization, we have discretized an active composite beam that is composed by a polymeric matrix with a defined number of SMA wire in itself in a bimaterial plate by using the relation 1. At this point on this section, it is possible to apply the momentum equilibrium and the non-interfacial debonding between the SMA layer and the polymeric matrix layer. And through this relation, it is possible to connect the stress generated during the recovery of the SMA material directly to the bending radius of the active composite beam. And from this relation, it is possible to obtain the tip vertical displacement of the active composite beam. At this point, we are not only interested in the vertical displacement of the tip, but we want to reconstruct all the deformed profile of this active composite beam. So for this purpose, it is necessary to apply the linear elastic beam theory, but this theory cannot be applied to materials that are not homogeneous on the section. So an homogenization of the section is needed, and the height of the section is maintained constant to preserve the strain distribution. At this point, we know from the previous relation, which is the value of the vertical tip displacement, and we can evaluate which is the load through this relation 1 to bring the beam at this vertical displacement. At this point, by varying the coordinate x along the length of this active composite beam, it is possible to obtain the full deformation of the beam along the full length. This model have to deal with large displacement, so it is necessary to evaluate also the horizontal displacement of each point of the along the length of the beam. The beam has been subdivided in different interval, and for each node, the vertical and horizontal displacement are calculated through the relation 2. At this point, to validate the analytical model, a first comparison has been done by taking some parameter from the literature. When I talk about parameter, I mean geometrical and mechanical parameter of the SMA material and the polymeric matrix, and also the dimensional parameter of the active composite beam. And by doing this, the model was fully implemented in MATLAB. And the first comparison, it is possible to obtain by comparing the stress generated in the SMA layer with a good agreement. Another type of comparison can be made on the vertical displacement of the tip of the beam. In particular, both the literature result and the analytical model that we have implemented show a maximum tip displacement for this geometry of around 30 millimeters with a maximum transformation temperature of 100 Celsius degree. Another comparison to validate the model has been made by using the experimental parameter that we have obtained for the experimental characterization that I previously talked about with a new geometry. And in particular, this parameter has been implemented in the ANSYS software, and the comparison has been made in terms of the deformed profile of the active composite beam. And also in this case, a good agreement of the analytical versus the numerical model is. And finally, the last comparison that we have made is based on experimental validation. In particular, we started by analyzing some 3D printed material by conducting different 3-point bending flexural test, and in particular we selected the 3 of this material that have an elastic module under 2 gigapascal, and in particular PETG, polypropylene, and PVDF. And by doing this, we have directly inserted the SMA wire during the printing process with the protection in with the microtube of Teflon between the surface of the polymeric matrix and the SMA wire. The prototype produced have not we have not obtained a good result from this prototype because all the material present an incredible delamination problem, and this is due the thermal increase in temperature when the SMA wire has been activated. And to solve this problem, we have redesigned a new active composite produced as 3D printed material. In particular, we introduced some intermediate support and terminal that are printed in carbon fiber reinforced nylon, and the base of the beam is made by PETG, and we have used in this time a special class of SMA wire that are silicon sleeved to insulate the SMA layer between the polymeric matrix and the SMA wire itself. Okay, it's the last one. At the end of this, here there is a video, but I think it's not work because there is the laser. Okay. Okay, so we have measured the deformation of this produced active composite beam, and we have compared the result versus the analytical mode with a good agreement, in particular with the maximum transformation strain in the analytical model of 5%. In conclusion, we can affirm that when we want to design active composite beam, the temperature play a really important role in the design of this particular type of material, and also the SMA material set the maximum transformation, the maximum target temperature needed for the actuation between the dependence on the stress, and also we have to choose correctly, which is the electrical current if we want to provide a joule heating not occur in an overheating, for example. Okay, thank you for attention.